In this video, we're looking at conservation of energy for what we call ideal systems. More on that in a moment. We want to figure out a formula for gravitational potential energy and then use that in our conservation relationships. We already know how to talk about kinetic energy. Motion causes objects to have this, and so we've got a formula for that. We also know how to quantify stored energy in a spring, which has to do with the work done on the spring to compress or stretch it. We can do a similar thing with gravitational potential energy. If you think about the work required to lift something up in the air, you have to apply a force at the very least equal to the amount of its weight in order to lift it up in the air. And as you lift it up in the air, you do work, and that work is stored as gravitational potential energy. How do we know the energy is stored? Well, you can get it back as kinetic energy if you drop it, right? So that's how we know. Now, our formula that we come up with gravitational potential energy comes from the fact that the minimum amount of force required to lift it is equal to the weight. And if we lift it at a constant speed, then those two forces will be the same. So the work done is equal to mg, the weight of the object, times h, the height you lift it up. And that all works out. That gives us units of joules. But this is really only good if little g is a constant near the surface of the Earth or another planet where you know little g on that planet. And m is pretty obvious. We know what the mass of an object is. But what about h? Where are we measuring our 0 point? It turns out it doesn't matter. You can pick 0 to be whatever you want. And in fact, as we will learn in a more complicated version of this a little bit later, infinitely far away from the center of a planet is where we call 0 when we're dealing with gravity in very large scales. More on that later. But we can pick the ground to be height 0. We could pick the height of a table to be height 0. We could pick the starting point to be height 0. Whatever makes your problem easier. So for example, a 50 kilogram woman stands on a diving board 1 meter above the water. What is her gravitational potential energy? With respect to the water, it's mgh, or 500 joules, 50 kilograms times 1 meter times 10 meters per second squared. But what if the pool is actually on the top of a building, right? This is a rooftop pool. And we now are going to ask, well, what's our gravitational potential energy with respect to the ground? Well, if the ground level is h equals 0, then mgh gives us 50 kilograms times 10 meters per second squared times 10 meters high, which gives us 5,000 joules of gravitational potential energy with respect to the ground. What if she falls into a 5-meter deep pit off the side of the building, right? Hopefully she's okay and lands on an airbag or something. Very impressive stunt actor, right? Well, if we call 0 the ground, then now she has negative 2,500 joules of gravitational potential energy, right? Less than she would have had at height 0. And so this is to illustrate that where you call 0 doesn't matter. It's okay to have negative gravitational potential energy because it still works. If you were to climb out of that pit, you would gain potential energy, right? Spring potential and kinetic energy can't be negative because of the way they're defined in terms of speed squared and displacement from equilibrium squared, but gravitational potential can. Does it matter how she gets into the pit? Not really, right? She could fall into the pit. She could climb down the ladder and walk into the pit. The result of how much energy she has at the bottom of the pit is the same either way. There's another thing to think about. You've probably heard of this demo in class. We may watch a video of it because I don't have the bowling ball set up. But why is the professor sure that when they release the ball from right at their nose, stand perfectly still, that the ball won't swing back and knock them out? Well, the reason for that is that energy is conserved, right? Energy is never created or destroyed. Unless you give it a push, do work on it to speed it up faster than it would go normally just by being released, it can only come back up to the original height. So let's look a little bit more at energy conservation. If you imagine some mass, some blob, right, and it falls down. If energy is conserved, where did it go? Because after it hits the ground, it's at rest again. It started at rest, had gravitational potential energy up there, then it sped up, and then it hit the ground. Well, it turns out that when things suddenly stop or when things are slowed down by friction or something like that, conservation of energy still applies. It's just no longer mechanical energy. It's no longer potential and kinetic, right? Joule, after whom we name the unit of joules, did some experiments where he allowed gravitational potential energy to pull a weight down slowly and pull a rope that was attached to this device. This was filled with a fluid. And basically, the motion of all of this, which eventually got slowed, right, because it was against the resistance of the water, he was able to measure an increase in the water temperature. So ultimately, when you lose gravitational potential energy or you lose kinetic energy, and it seems like it has been destroyed, usually what happens is it became heat or a transfer of thermal energy. Right? So when we talk about conservation of energy in our class, we're really talking about conservation of mechanical energy, which includes kinetic and potential. And so energy is conserved, no exceptions. And there's two types of systems: ideal systems, where just these three terms we've learned about are enough, or there's non-ideal systems. And we're going to focus on ideal systems right now, but we will say that any time that's violated, that probably it's thermal energy or heat. So mechanical energy, I've already said this word a few times, or this phrase a few times, and it's really just the sum of all the kinetic and potential energies that we have. So chemical energy, thermal energy, things heating up, mass energy like E equals mc squared, those things are not mechanical energy. They're still energy, and they're still part of the energy conservation conversation, but they are not mechanical energy. And if a system is ideal, that is, there's nothing non-conservative going on, more on that in a second, right? We can say that the initial mechanical energy equals the final mechanical energy. The kinetic energy plus the gravitational plus the spring at the beginning is equal to that at the end. They do not gain or lose mechanical energy. And the reason for this is that all of the forces that are involved, spring force and gravitational force, are a special type of force we call conservative forces. The kind of things where only gravity acts, a projectile, even a frictionless roller coaster. We have normal force, which isn't a conservative force, but on a roller coaster, it always acts perpendicular to the motion, so it does no work. The spring-loaded cannon, because a spring applies a force in a way that's predictable and understandable. So these different forces acting on the object just work to transfer energy around to different conservative or mechanical forms. So if you look at a projectile flying through the air, and we've analyzed this before, right? What forces do work on this projectile? Well, it's just the force of gravity pulling straight down. That's the definition of a projectile, right? Ignore air resistance. And so that means any gravitational potential energy you have, it can become kinetic energy or vice versa, because the force of gravity is pulling down, right? Initially, it's fired upward, right, with some kinetic energy, and gravity is pulling down, doing work to slow it, so transferring from kinetic energy to gravitational potential energy. And then once it reaches its peak, it all gets transformed into kinetic energy. So for example, right, if we start at 20 meters, this is a 10 kilogram projectile, so it's 2,000 joules of gravitational potential energy. If we go up to 40, it's 4,000, back down to 30, 3,000, 2,000, 1,000, and 0 joules when you hit the ground. And since the total amount of energy of mechanical energy is kinetic plus potential, we need to calculate that kinetic energy at the beginning, 1/2 mv squared, which is 4,500 joules. Well, now we have a total of 6,500 joules, which means the kinetic energy has to add to the potential to get to 6,500 joules. So at the bottom of the flight, when all of our energy is kinetic, it's going the fastest it goes just before it hits the ground. It's 6,500 joules of kinetic with 0 joules of potential, right? And so we can ask ourselves other questions about this. Once we know the kinetic energy at the top, we can use kinetic energy equals 1/2 mv squared to solve for the velocity. And we find that at the top, the speed is 22 meters per second. We already know that at the highest point, the velocity is parallel to the ground. It's all in the x direction. So we know everything we need to know about this problem. We can also do this kind of thing on a roller coaster, right? What forces act on the ball? Force of gravity and normal force. But only the force of gravity does work, because the normal force is always perpendicular to the path of motion. Which means the force of gravity, just like the projectile, helps transform between gravitational potential and kinetic. And we can figure out things based on what we know. If I tell you we start with 1900 joules of energy at point A at the top, where it's at rest, that means that's all of our energy, right? What is the mass of the ball? Well, we can solve for mass by dividing gravitational potential energy by GH, giving us 2 kilograms. Then we have everything we need to know to solve for the rest of this problem. We know that we start at rest, 0 kinetic energy, and we have 1900 joules of gravitational potential. As it goes down the hill, right, we get more kinetic and less potential until we are at the bottom where we have all kinetic and no potential. So how do we approach this kind of problem? What you do is you start by stating initial mechanical energy equals final, and that means kinetic plus gravitational plus spring equals kinetic plus gravitational plus spring. We have to decide where the initial and final are. We get to pick our 2 points. Ignore what goes on in the middle because that's not important for this equation. Take a picture of what's happening right in that moment. Is it moving? Is it up high? Is there a spring? If you can answer yes to any of these questions for either the initial or the final, then you keep that term. If it is not moving, the kinetic is 0 and you can cross it out. If it's not up on the high, if it hasn't been lifted up or down throughout the process, then the gravitational is the same at the beginning and the end, and you can cancel those out. If there are no springs or the spring is not compressed or stretched, those could be 0 as well. Get rid of anything that's 0, and then rearrange, simplify everything, isolate the unknown, and finally plug in your numbers. Most of these terms, well, gravitational and kinetic both have mass, so oftentimes mass will cancel out of one of these equations, which is nice. So we can simplify things that way. So, example problem. A spring-loaded cannon, it's not really a cannon, but you get the idea, it looks like a cannon, with a spring constant of 15,000 newtons per meter is compressed 80 centimeters and released, firing a 60-kilogram circus performer into the air. How high is she when her velocity slows to 10 meters per second? So we start with our conservation of energy equation. Initially, we'll call height at the beginning 0, which means gravitational potential energy starts at 0. We start at rest, so kinetic energy is 0. We only have spring at the beginning. At the end, there's no spring because it's been uncompressed. And so we can rewrite our equation with all the variables there. 1/2 kx squared is mgh plus 1/2 mv squared. Solve for h, plug in our numbers, and we end up with 4.6 meters. That is how high she is when her velocity is at 10 meters per second. So that is the basic premise for solving conservation of energy problems. You have to pick an initial and final point, make sure that mechanical energy would be conserved. That is, we're only dealing with forces that are conservative. At this point, that's just gravitational force and spring force. Anything else, we have to use the work kinetic energy theorem to figure it out.